Chapter 13. Chapter 13. And that is functional language features, iterators, and closures. All right. We can do this. Short intro, too. Rust design has taken inspiration from many existing languages and techniques, and one significant influence is functional programming. Programming in a functional style often includes using functions as values by passing them in arguments, returning them from other functions, assigning them to variables for later execution, and so forth. In this chapter, we won't debate the issue of what functional programming is or isn't, but we'll instead discuss some features of Rust that are similar to features in many languages, often referred to as functional. More specifically, we'll cover closures, a function-like construct you can store in a variable, iterators, a way of processing a series of elements, how to use these two features to improve the I/O project in Chapter 12, the performance of these two features, spoiler alert, they're faster than you might think, other Rust features such as pattern matching enums, which we'll cover in other chapters, are influenced by the functional style as well. Mastering closures and iterators is an important part of writing idiomatic, fast Rust code, so we'll devote this entire chapter to them. Okay, this chapter sounds important. We're going to learn about closures and iterators. Next. Closures. Anonymous functions that can capture their environment. Rust closures are anonymous functions you can save in a variable or pass as an argument to other functions. You can create the closure in one place and then call the closure to evaluate it in a different context. Unlike functions, closures can capture values from the scope in which they are defined. We'll demonstrate how these closure features allow for code reuse and behavior customization. More or less here they define what a closure is in a very abstract way. They said closures are anonymous functions that you can save a variable in or pass as arguments to other functions. And you can create a closure in one place and execute it later on whenever you feel like executing it. Evaluating it, but yeah, same difference. Creating an abstraction of behavior with closures. Let's work on an example of a situation in which it's useful to store a closure to be executed later. Along the way, we'll talk about the syntax of closures, type inference, and traits. Consider this hypothetical situation. We work at a startup that's making an app to generate custom exercise workout plans. The backend is written in Rust, and the algorithm that generates the workout plans takes into account many factors such as the app's user age, body mass index, exercise preference, recent workouts, and an intensity number they specify. The actual algorithm used isn't important in this example. What's important is that this calculation takes a few seconds. We want to call this algorithm only when we need to, and only call it once so we don't make the user wait more than necessary. We'll simulate calling this hypothetical algorithm with the function simulate expensive calculation, shown in listing 13-1, which will print calculating slowly. Wait for 2 seconds, and then return whatever number we passed in. Alright, so now we get to write some stuff. And I have my editor already open. And let's see what they have here. Cancel. So we're using standard library thread. I can spell this. And we're going to use standard library time duration. That makes sense. Time duration. And we're creating that function they mentioned, which is simulated expensive calculation. So function simulated expensive calculation. And it takes in intensity, which is a U32, the number that we pass in, and we're just going to return that number. And like they said, it's going to print calculating slowly, dot. And then in a thread, we're going to sleep duration. We need a duration. I see. Sleep takes a duration. That makes sense. From seconds, so our duration is going to be 2 seconds. And then we're returning the number that we passed in. That's interesting. That seemingly means that whenever we call thread.sleep, whatever thread that this function is being executed in currently will sleep for 2 seconds. Okay. So let's move on. Next is the main function, which contains the parts of the workout app important for this application. This function represents the code that the app will call when a user asks for a workout plan. Because the interaction with the app's front end isn't relevant to the use of closures, we'll hardcode values representing inputs to our program and print the outputs. So basically what they're saying here is that, yes, we're creating an example app to demonstrate closures, and yes, this example app, technically speaking, will need a front end. But because the front end will take away from what they're trying to demonstrate, we're just going to hardcode the values and pass over that. So let's see what happens next. The required inputs are these: an intensity number from the user, which is specified when they request a workout to indicate whether they want a low intensity workout or a high intensity workout. A random number that will generate some variety in the workout plans. Okay? The output would be the recommended workout plan. Listing 12-2 shows the main function we'll use. So let's see their main function. They have the simulated user specified value. So let's define that. Simulated user specified value. Let's say set the equal to 10. Okay. Then we have simulated random number. I mean, we could have just imported random and did that, but okay. I am not going to argue with you. So the simulated random number is 7. And then we have the function that we're calling, GenerateWorkout, which hasn't been defined yet, but I guess that's coming soon. GenerateWorkout. And it's going to take in the simulated specified value. And it's going to take in the simulated random number. And that is it. And this definitely should not compile because this function does not exist currently. We've hard-coded the variable simulated user specified value as 10 and the variable simulated random number as 7 for simplicity's sake. In an actual program, we'll get the intensity number from the app front end and we'll use the rand crate to generate a random number, as we did in the guessing game example in chapter 2. The main function calls a GenerateWorkout function with the simulated input values. Now that we have the context, let's get to the algorithm. The function GenerateWorkout in listing 13-3 contains the business logic of the app that we're most concerned with in this example. The rest of the code changes in this example will be made to this function. Alright, so summarizing what they said here, for simplicity's sake, they gave us the input values that would typically come from the front end of the application. So we just have that so we can pass it directly into our workhorse, which is the main algorithm, GenerateWorkout. And GenerateWorkout is going to hold all of our business logic and do most of the work. And that function is what we're going to write next. And here it is. So let's get to it. Function generate underscore workout. We have intensity U32 and we have random number, which is also going to be U32. It's not returning anything. Cool. So let's start writing. If intensity is less than 25, what do? We print today do blah 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 push-ups, and then simulated expensive calculation intensity. Okay. If the number is less than 25, today do push-ups. And then the variable that we're passing in, I guess this can be indented. That can be indented. Simulated expensive calculation, intensity. And then we have our else. Oh, nope. I missed it. This is not an else. So we have, if less than 25, we have the first print statement, then we have another print statement, then we have an else. So after the first print statement, we write the second one. Print next do blah 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 sit-ups. Simulate expensive calculation, intensity. Okay, and now we have the else statement. Else if round number equals 3, print line. I'll put this on a new line anyway. Take a break today. Remember to stay hydrated. Ooh. We have an else here. In the else, what do we have? Today, run for blank minutes. This is kind of intense. I mean, if the number passing is what, like 25? No, less than 25. I think the number is we're passing in is 10. Alright, so it's not that bad. 4 minutes. Intensity. So let's read through this real quick. Just make sure it makes sense. So you have GenerateWorkout, right? It takes an intensity, which is a U32, and a random number, which is U32. Currently, we have both of those hard-coded as 10 and 7. And I'm not sure why a random number is not showing up here, but okay. So if the intensity is less than 25, then we say do that many push-ups, do that many sit-ups. Else, so if the intensity is greater than 25 or equal to, we check the random number. If the random number is equal to 3, we tell them to take a break, hydrate. If it is not equal to 3, we tell them to run. So this is a pretty intense workout, and you can only get a break when the random number is equal to 3. And since we hard-coded at 7, this person never gets a break. And theoretically speaking, I think we should be able to run this, given that we have a main and all the functions are defined. Let's test that out. Cargo run. All right, so it did run. We have the, let me move this over again. So it ran, and we have calculating slowly, which is our simulated expensive calculation, and it waited for about 2 seconds. Today we do 10 push-ups. 10 was the hard-coded number we passed in. Next we do 10 sit-ups. 10 sit-ups was down here. And then we are done. We did this if block, and we came out of the function. It was over. All right, let's see what they say. The code in listing 13-3 has multiple calls to the slow calculation function. The first if block calls simulated expensive calculation twice. The if inside the outer else doesn't call it at all, and the code inside the second else case calls it once. The desired behavior of the GenerateWorkout function is to first check whether the user wants a low intensity workout indicated by a number less than 25, or a high intensity workout, a number of 25 or greater. Low intensity workout plans will recommend a number of push-ups and sit-ups based on the complex algorithm we're simulating. If the user wants a high intensity workout, there's some additional logic. If the value of the random number generated by the app happens to be 3, the app will recommend a break and hydration. If not, the user will get a number of minutes of running based on the complex algorithm. This code works the way the business wants it to now, but let's say the data science team decides that we need to make some changes to the way we call the simulated expensive calculation function in the future. To simplify the update when these changes happen, we want to refactor this code so it calls the simulated expensive calculation function only once. We also want to cut the place where we're currently unnecessarily calling the function twice without adding any other calls to the function in the process. That is, we don't want to call it if the result isn't needed, and we still want to call it only once. Alright, so the first part of this was just going over the function, how it works, right? But the second part is prepping us for the refactor. And they want to refactor in the following ways. They want to call this simulated expensive calculation once, which makes sense because it's an expensive call. And in the cases where we don't need to call it, we don't want to call it. And they marked out that currently we're calling it like 3 times. We have it in the first if block twice, here and here, which I guess could be moved into one. And then we're calling it here at times, which, okay. So let's see how we're going to refactor it. Refactoring using functions. We could restructure the workout program in many ways. First, we'll try extracting the duplicated call to the simulated expensive calculation function into a variable as shown in listing 13-4. I see. So let's go over here, make that smaller. There we go. And let's extract that out. So the generate workout at the very top. We're making this a variable. So let expensive result equal simulated expensive calculation, pass in intensity. And now that we have that, we can just plug that in places. So this call, not needed anymore because we saved the result. Bam. Same thing here. Same thing here. And with that one change, we broke down 3 different calls to one explicit call, and then save the result, and then pass that result in when needed. Makes sense. This change unifies all the calls to simulated expensive calculation and solves the problem of, first, if block, unnecessarily calling the function twice. Unfortunately, we're now calling this function and waiting for the result in all cases, which includes the inner if block that doesn't use the result value at all. Makes sense? So what they're saying here is, yes, this is a good refactor. Yes, this makes sense. However, there is a downside to this. This block needs the expensive result. This block needs the expensive result. but this one down here does not. And even though this does not need the expensive result, it's still waiting for the expensive result to be calculated. That seems like a waste of time. And that's what they're pointing out here. Why are we wasting time on this case? Why does this case have to wait for this call to be done? No need, there's no dependency. So, we want to define code in one place in our program, but only execute that code when we actually need the result. This is a use case for closures. All right. Refactoring with closures to store code. Instead of always calling the simulated expensive calculation function before the if blocks, we can define a closure and store the closure in a variable rather than storing the result of the function call. As shown in listing 13-5, we can actually move the whole body of simulated expensive calculation within the closure we're introducing here. And this is the expensive closure. So they took what this function is and then moved it into a closure, and this is the syntax for it. Alright, so let's write this. So this is no longer needed. And instead, we have this syntax. We have the number, and it's being passed into this closure. Print calculating slowly. ... And we're still doing the thread thing. So thread sleep, and that takes a duration. You have a duration from seconds. 2 seconds. And then we're returning the number that was passed in, which is the 2. I kind of want you to be indented. Shouldn't you be indented to here? The closure defined comes after the equal to assign it to the variable ExpensiveClosure. Oh, they even changed the name? Hold up. Missed that. Ah, they called it ExpensiveClosure. So they didn't rewrite this? And now expensive result doesn't exist. Just in case, I'm putting expensive result back. Moving on. The closure defined after the equal sign to assign it to the variable ExpensiveClosure. To define a closure, we start with a pair of vertical pipes inside which we specify the parameters to the closure. This syntax was chosen because of its similarity to closure definitions in Smalltalk and Ruby. This closure has one parameter named num. If we had more than one parameter, we would separate them with commas like param1, param2. Okay, so they're going with some of the syntax, and the syntax is taken from Smalltalk and Ruby, which are great languages, and that is the pipe syntax. So we have the pipes, that thing, and this thing, and we put our parameters inside of it. I didn't mean to change that. Pipe num. And then this parameter seems to be captured within this code block and used. Cool. After the parameters, we place curly brackets that hold the body of the closure. These are optional if the closure is a single expression. Oh, I hate that. Those are so annoying because then you're not really sure if the body is the body or not the body. So what they said in this sentence, because this sentence needs to be unpacked, is that yes, this closure has these brackets that designate the body. However, if the closure is just a single line, you don't need to put the curly braces because it's just one single line. It's easy to read. Personally, I don't like that because I like to see it explicitly, but syntax to syntax. The end of the closure, after the curly brackets, needs a semicolon to complete the let statement. The value returned from the last line in the closure body, num, will be the value returned from the closure when it's called, because that line doesn't end in a semicolon, just as the function bodies. So what they're saying here is you need a semicolon at the end because that completes the let statement. But in here, we're more or less following the syntax of what we do for functions. The semicolon means nothing's going to be returned, and not having semicolon at the end means that statement is going to be returned. So yeah, we're returning num in this ExpensiveClosure. Note that this let statement means ExpensiveClosure contains the definition of an anonymous function, not the resulting value of calling the anonymous function. Recall that we're using a closure because we want to define the code to call at one point, store that code, and call it at a later point. The code we want to call is now stored in ExpensiveClosure. Okay, that was kind of thick, just in terms of wording. What they're saying here is that this variable, ExpensiveClosure, is a reference to an anonymous function. It is not a reference to the result of this anonymous function. So earlier when we were writing expensive result, we stored the result here and then we pass it through. That's not going to work in the same way, or ExpensiveClosure is not going to work in the same way because it's not doing the same thing. This was a stored result. This is a stored function call. And you kind of see it in syntax right there. Function, question mark, pointing to question mark. With the closure defined, we change the code in the if blocks to call the closure to execute the code and get the resulting value. We call a closure like we do a function. We specify the variable name that holds the closure definition and follow it with parentheses containing the argument values we want to use, as shown in listing 13-6. Alright, so rewriting this so we can use our closure. So this line can definitely disappear. And our closure syntax is, well, using a closure like using a function. ExpensiveClosure. And we pass in the thing that we want to use, the parameter, which is num. And we do that a few times. So copy. So we place it in those three places, and hopefully this should work. Moving onward, let's try to run this. We have a warning, which is probably because we have a function that is not being used. We have dead code, so yeah, we wrote this function. It is no longer being called. You can probably delete it. I'll delete it now. You can go away. We don't need you anymore. And then the second warning was create Rust closure should have a snake case name. They're complaining about the name of my file. Meh. And then everything else worked as expected. Calculating slowly. Today, do 10 push-ups. Calculating slowly. Next, do 10 sit-ups. Okay. Now the expensive calculation is called in only one place, and we're only executing that code where we need the results. However, we reintroduce one of the problems from listing 13-3. We're still calling the closure twice in the first if block, which will call the expensive code twice and make the user wait twice as long as they need to. We could fix this problem by creating a variable local to that if block to hold the result of calling the closure, but closures provide us with another solution. We'll talk about that solution in a bit. But first, let's talk about why there aren't type annotations in the closure definition and the traits involved with closures. Okay, so here what they're saying is And using this closure, we reintroduce one of the problems that we were trying to fix. And that is, we're now calling this closure, this expensive piece of code, multiple times when we don't need to. So in this first if block, we call it twice. Unnecessary, but we're doing it. Second if block, we only call it once. We've solved the problem where if we get to this block is no longer waiting on ExpensiveClosure to run because it's not being called at all. But the trade-off is that in this if block, we now have to wait twice as long for it to calculate. Not great. And to see that, we can just run this and just count ourselves. This will be about 4 seconds. Ready, set, go. 1, 2, 3, 4, boom. Yeah, about 4 seconds. Twice as long. Not good. But before we go over any of that and how we want to refactor it, take a step back. So how do we change this? One way, and probably the most obvious way to do this, is that in this if block, we could create a local variable, let's say right about here, that holds the result of the ExpensiveClosure, and then we can use it twice. We can use it in here and here, just pass it in. That makes sense. That is a workable solution, reasonable solution, but they want to demonstrate some of the closure features, and I'm interested to see what it is, that can also solve this problem. So there are more than one way to solve this problem. They just want to show us an alternative. But the whole local variable thing makes sense.